the way every day goes.
Hello everyone. In this group project, we focus on Rapid KL My Rapid bus scheduling. The goal was to create a system that helps bus run smoothly without overlapping trips or delays. We found that scheduling is essential in managing resources and avoiding conflicts, especially in public transportation, where timing is very important. If the schedule is not clear, bus might arrive at the same time or be late, which causes problems for passengers. To solve this, we developed the project in Google Colab using Python and also Google OR tools. So these tools help us build a smart scheduling system that can manage many bus routes more efficiently. To build our schedule, we used a graph theory concept called graph coloring. So this method helps us avoid conflicts by giving each bus route a different color or time slot so they don't clash with each other. So by using this method, we were able to develop an optimized timetable with no overlapping trips. That means all buses have their own time and everything runs more smoothly. We also found that analytical tools or computational tools help solve real problems in bus transportation, especially like making sure bus arrive on time. So this system ensure better planning and reduce late arrival, which make it more reliable for the public. So overall, this project shows how simple tools and ideas from maths like graph theory can help solve real-world problems in transportation.
In this project, we focus on addressing some key challenges in the Rapid KL bus system within the Sungai Besi area. Even though there are many bus routes available, commuters often experience issues like delays, bus bunching, and congestion at major terminals. So these problems are usually caused by poor scheduling and overlapping routes that are not properly coordinated. So, what exactly are we trying to solve? Our first objective is to identify and analyze road conflicts among the Rapid KL bus routes. So many of these roads share the same roads or terminals, and that create scheduling conflicts. For example, when several buses use the same terminal or arrive at the same time, it causes crowding, longer waiting periods, and even service delay. So for our second objective is to improve scheduling efficiency. We want to avoid overlaps in bus routes and assign appropriate time slots to the buses run smoothly without interfering with one another. By using graph theory and coloring algorithms, we can make sure that no two conflicting routes operate at the same time. Lastly, our third objective is to reduce the chance of bus bunching and terminal congestion, especially at critical hotspots like Lebuh Pudu, Stesen LRT BK5, and Bandar Tasik Selatan. These are key connection points, and if scheduling is not managed well, it leads to overcrowding, delays, and poor commuter experience.
Next, I will explain the solutions for the three objectives in our project. So, for the first objective, which was to identify and analyze route conflicts among Rapid KL bus routes in the Sungai Besi area, we applied graph theory to model the bus network. Bus stops were represented as nodes and routes were treated as edges. Using Google Colab and OR tools, we analyzed overlapping routes and constructed an adjacency matrix and a network graph to visualize these conflicts. This helps to identify which routes could cause scheduling issues due to shared path or terminals. Next, the second objective aimed to improve scheduling efficiency by minimizing overlaps, delay, and congestion. To achieve this, we apply a graph coloring algorithm with OR tools in Google Colab. This allows us to assign different time slots or colors to conflicting routes, ensuring they did not operate simultaneously. This resulted in a conflict-free timetable that improved route coordination. Finally, for the third objective, which was to reduce bus bunching and terminal congestion, The timetable grouped non-conflicting routes into separate slots. This approach prevented multiple buses from arriving at busy terminals like Lebuh Pudu, Stesen LRT BK5 and Bandar Tasik Selatan at the same time. As a result, we achieved smoother bus flow, reduced waiting times, and optimized terminal operations. In summary, our solutions show how graph theory, Google Colab, and OR tools can be applied effectively to solve real-world transportation scheduling challenges.
Now I will be presenting the graph representation of our bus scheduling problem using graph coloring technique. This graph represents the relationship between different bus routes based on scheduling conflict. Each node in the graph corresponds to a specific bus route, and edges indicate that those routes cannot be assigned to the same time slot due to overlap. As we can see, each node is labeled with the route number and its assigned time slot. For example, route 1 for slot 1 or route 15 for slot 4. These time slots are determined in a way that avoid conflict between two connected routes. The nodes are color-coded based on their assigned slot. For example, green for slot 1, blue for slot 2, gray for slot 3, and also yellow for slot 4. This makes it easier to visually confirm that no adjacent nodes, meaning that no conflicting routes share the same color or slot. The edges or the line connected the nodes represent conflict, which means that the two routes are not allowed to operate at the same time. This is a typical application of a graph coloring problem, where the goal is to assign the minimum number of time slots so that no two adjacent nodes have the same slot. In this case, we were able to schedule all routes using just 4 different time slots. By using this approach, we efficiently minimize conflict and ensure an optimal schedule for all routes. This method is scalable and could be applied to a larger system like bus or train network, or even class scheduling in universities. Here we have our final timetable that was generated based on the graph coloring solution shown earlier. The table summarizes the route assignment into 4 different time slots, which are also represented by different color for easier visualization. In slot 1, marked in green, we have route 1, 3, 6, and 13. Slot 2, we have route 2, 5, 9, and 10. Route 3, in gray, we have 4, 7, and 11. And finally, slot 4, in yellow, is assigned to route 8, 12, 14, and 15. This timetable ensures that no two conflicting routes are scheduled in the same time slot, meaning that our schedule is conflict-free and efficient. This result was made possible by applying graph coloring, where we minimize the number of slots needed while ensuring no adjacent nodes share the same slot.
To conclude our project, we successfully applied graph theory and Google OR tools to solve a bus scheduling problem involving rapid KL routes. By identifying conflicts between selected routes, we managed to generate conflict-free timetable that avoids overlaps and improved scheduling efficiency. So this shows how computational methods like graph coloring and optimization algorithm can be used to solve real-life problems, especially in public transportation planning. However, we also acknowledge several limitations. The data we used was static and not updated in real time, and we did not include certain real-world constraints like traffic, bus availability, or driver schedules. Despite this project, demonstrate the potential of mathematical approaches to improve route management and resources allocation in public transport system.